Hi, I'm Abhinav and this is a video on baseball and physics. I went to a public lecture by Alan Nathan and he was talking about the physics of baseball and how we can learn a lot from just watching the game. And before I begin, I would also like to thank a couple of other people who helped me out directly and indirectly on this project. I would like to talk about the coefficient of restitution, the trampoline effect, and dynamic lift. And before we begin, I just want to point out that I'm not an expert on physics, and it's possible that I may have made many mistakes while understanding these ideas. If you find anything wrong, just let me know, leave a comment or email me. And let's start with the coefficient of restitution. You may have seen this in collision problems, and well, baseball involves the collision of a bat with a ball, so I think we should start with a definition of this coefficient. It's defined as the speed of separation divided by the speed of approach. Let's see what that means. We'll take a simple case of two balls colliding, and we'll talk about this collision before and after the balls actually collide. So let's first consider the before collision case. You have two balls, one with mass m1, the other one is m2, moving towards each other with speeds v1 and v2 initial. And the speed of approach in this case would be v1i plus v2i. Now, please note that I'm not using vectors. I'm just talking about speeds over here. And in this particular case, where they're moving towards each other, you can see that the speeds sort of add up. So it's like if you were the first ball and you were looking at the other ball, it will be moving really fast towards you. And if you started running towards this other ball, it would get even faster. So we're adding up those speeds. Let's come to the second case now, after collision. Let's say that the balls end up moving with velocities v1f and v2f, and the speed of separation, or how fast they're moving away from each other, in this case would be v1f plus v2f. And I want you to sort of think about this and take a few examples. Look at something moving away from you, then start moving in the opposite direction. You'll see that it gets faster. So that's why we're adding them up. Also note that the exact expressions that we use for this coefficient of restitution may change depending on how your initial speeds were oriented, whether you're adding them or subtracting them. So that should not be a problem. Now, the coefficient of restitution is also denoted by the letter E. And let's try to apply this definition for a simple example. If I told you that E for a collision was 0, what does that tell us about the situation? If you apply the definition, it's clear that it means that the speed of separation would be 0. Which is like saying that the two particles that we had that were colliding would get stuck together, and this is an inelastic collision, because they're not moving away. There's no separation anymore. And you could also work out elastic collisions by using an E of 1. On to the trampoline effect. I'll use the example taken by Professor Allen in his lecture. If you had a loose tennis racket, the strings are really loose, and you also had a tight tennis racket, and you had two tennis balls, and you drop these on the rackets, what would you expect to see? Which ball do you think would rise higher up? Guesses? Well, you can take a look at what happens. Let's try to explain why this happens. When you have the loose racket, you have the capacity to store a lot of energy. Your strings can easily stretch, and they'll take away the ball's energy and then return it to the ball. So you don't lose anything much. But in the case of the tight racket, you cannot really deform these strings. So what ends up happening is that the ball gets deformed, and this makes the ball lose a lot of energy, and this cannot be returned. It's just lost into thermal and vibrational energies. So you lose a lot of energy, and you cannot rise up as high as the ball rising with the loose racket case. I'm personally not very satisfied with the loose racket example, and I hope I can come up with a better explanation soon. Now let's get to dynamic lift, and I would actually recommend that you read a few pages from this textbook. It is my favorite physics textbook, and I'm not sure if you can get it easily because I had a lot of trouble finding it, but it's a really good thing. And it's page 357 if you want to read about dynamic lift. I'll follow the book's approach and we will discuss two interesting motions. Think of a ball or a knife moving through air, or in this case peanut butter, in two different scenarios. In the first one, you just have the knife moving in a straight line, no spinning at all. In the second case, you have the knife just spinning. In the third case, you superpose these two motions. In the snapshot from the first case where we had the knife translating without any rotation, I want you to notice this layer of peanut butter that is coming along and moving with the same speed as the knife. This is called a boundary layer. It has a key role to play in dynamic lift. Now when this boundary layer gets to encounter our spinning knife, spinning in the way that it's spinning in this case, you can notice that the upper portion of the peanut butter would have to move faster. It's like the spin speeds up the peanut butter, but the lower portion would be slowed down because of the spin. And when you take this idea and apply Bernoulli's equation, you get dynamic lift. And as I do not understand Bernoulli's equation very well, I will not try to explain it, but I would recommend that you search it up on Wikipedia.